All right, what L'Hopital discovered was an alternate way to find a limit. And you're probably wondering, why on earth are we going back to limits? Why didn't we learn this from the beginning? And that is because it involves taking a derivative. So first off, I want to find this limit algebraically. And the first thing that you do when you try and find a limit is just plug in the value that x is approaching. So if you just plug in a value for 0 for x, you get e to the 0, which is 1 minus 1 all over 0, which equals 0 over 0. And remember that that doesn't mean that the limit doesn't exist. That's one of those indeterminate forms. 0 over 0 is indeterminate. And normally what we did in Chapter 1 when we learned limits is that we would take some sort of algebraic method to manipulate that. Maybe factor it, maybe find a common denominator if there were fractions in it, maybe multiply by the conjugate, something like that. But this doesn't really fit any of those cases. All right. If you were to do this on the calculator, and I'm not going to take the time to pull up the calculator, but you could do it on the calculator and find the limit using the table, we would actually get 2. And hopefully you remember, you can put it into y equals and then start your table at x equals 0 and make your table set really, or the change in your table really, really small. And you would end up with 2. All right, but what L'Hopital discovered was L'Hopital's rule. Funny enough. And what L'Hopital's rule says that if you're taking the limit as x approaches some value of a function divided by another function and it produces an indeterminate form, and not only is 0 over 0 an indeterminate form, but also infinity over infinity is indeterminate. So if you get either of those two, then what you can do is that limit is the same thing as taking the derivative of the top and taking the derivative of the bottom and then finding the limit. It's just literally you take the derivative of the top, take the derivative of the bottom, and then find the limit. So since I got 0 over 0 by direct substitution here, then what I'm going to try and do is take the derivative of the top and the derivative of the bottom. So what would the derivative of the top be? 2e to the 2x, and the derivative of the bottom is 1. So now when I plug in a 0, I get 2 times e to the 0, or 2 divided by 1. And that's your answer. And just like we did limits the first time around, I am going to be picky about the notation. So make sure that you keep writing limit as x approaches 0 until you actually plug in that 0 and find that limit. And the key to this is that you have to get that indeterminate form first. You can't just automatically, you don't get the right answer if you start with something that's not indeterminate and you try and take the derivative of the top and the derivative of the bottom, you'll get the wrong answer. So it's got to start off as indeterminate. Yes, it'll work for anything that's indeterminate. So like on number 2, if we plug in, this is the limit as x approaches -1, and you would get 1 plus 1 minus 2 is 0 over 0. This problem would have been totally fair game on the Chapter 1 test, because what would we have done? Factored it, right, factored and canceled. And you may still be more comfortable with that, and that's fine, but now knowing L'Hopital's rule, since we know how to take derivatives, the derivative of the top is 2x minus 1, and the derivative of the bottom is 1. So as x approaches -1, I get -3, and I'm done. Yeah, it's quick. So personally, I would rather take a derivative of a polynomial than try and factor it. All right, number 3. Set the limit as x approaches -infinity. All right, so if I use direct substitution, -infinity squared will basically give me what? Infinity, right. And then, yeah, well, infinity squared is still considered infinity. And then e to the negative infinity is just e to the infinity, which 2.718 to the infinity power is also infinity. Okay, so this is our other indeterminate form. So since I have infinity over infinity, now I can use L'Hopital's rule. The derivative of the top is 2x. What's the derivative of the bottom? Negative e to the negative x. Okay, now when I plug in negative infinity, what do you think 2 times negative infinity is? Negative infinity. And then I'm going to get negative e to the infinity. And a negative divided by a negative is still a positive. Okay, so I still have an indeterminate form. What do you think I could do? Let's just do L'Hopital's rule again. And it will work this time. I promise. I won't make you do this multiple times. So go back to when we did the first derivative. So the derivative of the top is 2. The derivative of the bottom is e to the negative x. Now when I plug in negative infinity, I get 2 over infinity, which is what? 0. All that work for nothing. Yes, because of that x squared is why you have to do it twice. So, and not only, number 2 had an x squared in it, and we got away with only doing it once, but for that problem, because the top was x squared, that's why we had to do L'Hopital's rule more than once. So don't be afraid, as long as you get that indeterminate form again, don't be afraid to use L'Hopital's rule again. Yeah. Okay, number 4, limit as x approaches infinity of e to the negative x times the square root of x. If you use direct substitution, you're going to get e to the negative infinity and then the square root of infinity. Which, what do you think about that? It's infinity? Okay, it's infinity over infinity because even the square root, because what I can do is I can rewrite this as the square root of infinity divided by e to the infinity, bring that negative exponent down to the bottom. The square root of infinity is still infinity. If you've got an unbounded number and you take the square root of it, it's still going to be unbounded. So we really do have infinity over infinity. But another thing for L'Hopital's rule, in order for that to work, is that you need to start with a function divided by another function. So what would be a better way to rewrite this problem? Yeah, the square root of x over e to the x. And since that was infinity over infinity, now I can use L'Hopital's rule. All right. Derivative of square root of x. Yep, 1/2 x to the negative 1/2. Love the derivatives of e to the x. And the integral of e to the x, for that matter. Before I start plugging things in, I'm going to rewrite this as 1 over 2 e to the x, x to the 1/2. Especially when you have limits as x approaches infinity, I prefer to not use negative exponents. So if x is approaching infinity, what is that limit? Basically have 1 over infinity, so 0. So 4 was fairly, 4 I think you probably would have intuitively kind of come to that conclusion on your own. But it wasn't set up immediately as infinity over infinity, so we had to kind of work to get it as infinity over infinity. If for some reason that you think, I'm going to try for infinity over infinity and that's not working, then try and manipulate it into 0 over 0.